6, which is what we stopped last time. So we want to discuss the honeycomb structure, which is one kind of a typical kind of composite structures. Yeah, in this figure, we will see the typical architecture of a sandwich composite panel. It consists of a top surface, a bottom surface, it's a face sheet, and a lightweight core, typically honeycomb. It could be other structure. In the tutorial, we use a rectangular or square comb. And there will also be thin adhesive layer bonding the skin to the core. Yeah. Uh, After the fabrication, these components act together as an integrated structure system. And this configuration is widely used in aerospace applications such as fuselage panels, uh, control surfaces, uh, board structures. And the key idea is not simply material substitutions, it's a structural efficiency stereogeometric. Uh, in abaqus, if we want to simulate this structure, actually we need to simulate one by one. So the face sheet or the skin, we could simulate it as solid elements or solid material, bulk materials. Uh, the core is often modeled as shell elements. Yeah, and also the face sheet can be modeled as shell element as well. And for the adhesive, you could, if you don't want to model it, it's totally fine. You can just extract the stress to see whether it will fail at this point. And if you do want to model it, you could use a cohesive surface or element deletion for these two kind of materials. And let's look at the lower figures, which illustrates the stress distribution under bending, which is the most typical loading condition. When bending loads are applied, the top surface sheet will carry compression, as we know. The bottom one will carry compression, and the top one will carry tension. And the core will primarily carry transverse shear. If you're related to the Euler ballooning beam theory, you can remember that the top and the bottom will undergo large tension and compression, and in the middle, it will undergo a shear stress. Therefore, the face sheets are separated by a relative large distance to better handle the compression, because compression is mainly consists of tension and compression. Since bending stiffness scales with the square of the distance from the neutral axis, increase the panel thickness dramatically increase the rigidities, even if the core material itself is soft. So we could use pretty soft material as the core, but it has to be pretty shear resistant. In the simplest form, bending stiffness scale with the approximately like this. EF is the face sheet modulus, TF is the face sheet thickness, and H is the total sandwich thickness. You can see that increase the sandwich thickness dramatically increase the bending stiffness of the whole sandwich structure. And actually, the core contribute little to the bending stiffness directly. The main role is to stabilize the skin and carry shear. Under different loading conditions, yeah, it could have the sandwich structure could have different failure mode because the face sheet will experience large in plane normal stress and the core experience nearly uniform shear stresses. They will face differently. For example, under bendings, because the surface sheet is under tension and compression. So with compression, it will have, with tension and compression, it will have face sheet yielding. With compression, it will have face sheet winkling. It's kind of like a Euler buckling effect. With compression, purely compression, it will also have this winkling effect. With large shear force, the face sheet wouldn't deform too much, but the core will undergo large core shear and will fracture in a 45 degree. And also keep in mind that under some circumstances, we may have a core indentation with some object drop to the face sheet. And also, there's one thing to mention that is the adhesive layer. The adhesive interface mainly experience combined shear and pure stress. So therefore, it will undergo a mode 2 and mode 1 opening as a cohesive failure or crack opening. With all this add together in the sandwich structure, the stress is highly localized in the skins. The core primarily acts as a shear web, and the difference directly influences the failure mechanism. Great. From a design standpoint, sandwich structures optimize geometrics rather than material anisotropy. In the last week, we talked about laminates. Laminates tailor stiffness through fiber orientation, but sandwich panels amplify bending stiffness through separation distance. This geometric amplification is the primary reason for their widespread use in aerospace. However, this efficiency introduces complexity. The local instability must be considered, and the interface integrity become a critical issue. The core shear deformation may dominate the deflection. In a modeling sense, the modeling approaches depend on the design questions. For example, if we just want to understand the sandwich structure in a global structure response, then we could use equivalent sandwich cell sections, directly input the uh, shell behavior into the shell element. And therefore, we can capture the effective bending stiffness and the deformation of the plate or the panel itself. And if we want to go deeper, we want to understand the core shear and the detailed stress analysis, then we need to model the skin and the core as separate layers. And we need to use oftenly we use orthotropic material for the skins and use orthotropic or crushable form for the core. If we want to even proceed a debonding analysis, then we want to introduce the cohesive element between face sheet and core and introduce damage initiation and evolution. And in that sense, mass consideration are important because there will be high stress deformation and that cause shear locking. The core nonlinearity can affect convergency and the softening behavior because of the plasticity will require other stabilization process. So then let's look into an example. Uh, oh, sorry, I hide this one. Let me uh, occur this one. Great. So here's our example. I select such a structure and dimension from these two paper from Professor John Hutchinson and his student. And Professor John Hutchinson is the academic great grandfather of me, so it's my honor to use his paper as a tutorial section. So we will form such a square comp structure, yeah, with steel. Yeah, here I have the now with aluminum alloy. List the material property here, and because of the plasticity, we will use Johnson Cook model for the plasticity. And here you can see how they build such a structure. Yeah, it's all made from the same material, the aluminum alloy. They use a laser cut to bring this core and assembly together and adhered. I think it's welded with the face sheet, and therefore they can undergo some TNT blast and deform like this. So at first we will try to calculate the simple loading case like bending, uh, compression, and shear. And later we'll see whether we could model the TNT blast uh, property. Okay, great. So let's go to abaqus. And similarly, I will put my structure here. This is the geometry we want to look at. Yeah, I will place it somewhere here. Or later I need to take a look at it and the material property. Okay, great. Now we have everything. Get it smaller. Now we start to get into abaqus. Oh, great. So first, uh, let me set my work directory to week 9. Yes. Okay. And let's open another folder. I would say Monday. Okay, great. So first, we want to use, let me take a look at this one. So you can see everything is in millimeters. So we use the millimeter unit system. We build a phase shift first. Because of the symmetric, we will only build a quarter of the structure. So first we need to use solid. The approximate size will be 1000. Yeah, it's deformable phase sheet. So first, let's draw an square. Doesn't matter. Yeah, let's put it there. Let's fix it. Fix this point, right? And we can change the dimension here. Will be 610 divided by 2, and it's 305. And also here, 305. Yes, you can type in equation as you want. Then this will be our phase sheet. The thickness will be 5. Let's change our part name as phase sheet. Great. Then next we need to build a honeycomb structure. Then now we need to use a shell structure, extrusion also. The total size will be 305, the same. Yeah, and it has to offset by 30.5. Okay, so because we are using a symmetric, so at first we will draw a line here. The starting point will be 30.5 divided by 2. Oh, we don't allow that. Then we will use somewhere here. 34 divided by 2. Then will be 15.25 and 0. And we want it to 15.25, 305. Great. So this is the vertical one, and we also build a horizontal one. That will be 0, 15.25 to 300.5, 305, 15.25. Great. Then next, let's do a linear pattern. This one, done. You can see that you already helped me to select the direction 2. Number is 10. We have 10, right? The spacing is 30.5. Great. Yeah, because I've built it earlier, so it's automatically showing like this. Now for the vertical one, similarly, we just wanted to have 10. Okay, great. Then we have our uh, honeycomb. We will extrude it like 51 millimeter. 51. Okay. Then this one will be our honeycomb or core. Great. Then let's go to property. What's the thickness here? Now we have utilized all this dimension. We want the other dimension there. The thickness of the the honeycomb structure. It will be great. Let's build a property first. Uh, let's put all the property into it, including density, because later we want to do an explosion. That is a dynamic calculation. So we do need the density. We are under millimeter, so density will be under. Let me check on the abaqus unit system. Okay, great. Also have the unit system here. So for density, we should use ton per millimeter. Now is kilogram per square meter square. Then let's do a calculation. So first, let's type into this one. Aluminum alloy is 7850. Then change from kilogram to ton. Need to divide it by 1,000, and change to meter cube to millimeter cube. We need to times divide it times or divide times 10 to the power of each. It's 9 times. Wow, that is pretty large. Ton per millimeter. I should divide it by 1 to the power of 9, right? Yeah, it's pretty small. It should be pretty small. Okay, great. That is the density, and we want elasticity. Young's modulus is in Pascal, megapascal. Then will be 161 G3. Poisson's ratio 0.35, and we want to add plasticity. For the plastic, we will use Johnson Cook. A here is already in megapascal, so let's put in 400. B is 1500. N is 0.4. M is 1.2. Melting temperature is 1800. Transition temperature is 293. Okay, great. And we need to add sub-options, rate dependent. We'll use Johnson Cook. C value is 0.045. If Shannon dot at 0, it will be 0.001. No, 001. 0.045. Yeah, everything is correct. Great, great. So let's call this material as AL6XN. I don't know what that means. Let's put it right there. Okay, great. So first, let's create a section for the face sheet. It's solid, homogenized, right? And also a section for the core, also homogeneous. Now we need to add the shell thickness. Here is 0.76. The 6 here is how they folded and welded to the face sheet. So we use the original one, 0.76 in millimeter. Great. Yeah, everything is by default. Then everything is done. We could cancel this and assign section. This one creates that core. The only material could be core from section middle surface, right? And also for the plate, let's call it face sheet. Oh, we forgot. Uh, tools. Do we have set manager? Oof, why don't we have set manager? Okay, I didn't add to it. Face sheet. Done. Section will be face sheet. Great. So now it's green. So next, let's double check on the orientation, local orientation. So later we want to calculate the stress, then we need to know the uh, local orientation. Then is no, this is for beam. Yeah, assign material orientation. This one. Don't have any other option. Assign. Okay, assign property. Let's select all of this. Done. Using default orientation and other methods. So let's zoom in. So you can see that one direction it's in plane direction for the whole sandwich structure, and two direction will be the out of plane direction for the whole in the thickness direction. I would say in the thickness direction of the sandwich structure. Then let's keep in mind that S11 will be the in plane stress, S22 will be the out of plane stress, and N will be 0 because it's plate. Yeah, it is. Okay, let's continue. Uh, so let's go to assembly. Let's put in this two, the core and the face sheet. It should align automatically. Great. And we need to offset the core by the thickness of the face sheet is 5. So we'll be adding 5. Okay. Then we add another face sheet. And we move this face sheet. Oh no. 4. 51 point plus 5, then will be 56, right? And it's done. Go to this. Let's go to step first. So first we want to calculate a statics general case. Let's use large deformation. Great. Uh, it will automatically have the plasticity field output. Yeah, you can see that. It already have the plastic. Yeah, this PEEQ, and PEMAG here is for the plastic. Then we don't need to modify it. It's great. Let's go to interaction. So first we want to build a interaction between the face sheet and the core. So because we don't want to model the adhesive, so we just directly tie it together. Use tie. Then one is top. We use tie. Let's use surface. We will select this surface. Let's call it top face. Done. And we also want to the surface for the core. Then we could say core, top core. Then this is a little bit confusing. This one, this sheet. Let's suppress this one. Right. Oh no, the other one. No, suppress. It's not a good way. We'll hide it. Then we have to select the this one by one. I have tried to like directly select it, but it seems it didn't work in the surface selection. So, for example, I would like to select like this, then it will select this surface. Yeah. If I deselect, then the whole surface is gone. Even this line is gone. So we have to select one by one. Yeah, it's a little bit troublesome. So we have select all this. Let's do this one by one. It might take 5 to 10 minutes for selecting this. Uh, in real application, we could build a Python script to fast select this. But now, just for tutorial, building a script is even slower. Yeah, so for large amount of selection, you should build a Python script to select that. But with only like 1,000, no, 100 or 200 selection, then actually select by your hand is even faster. Although it's annoying, as the way actually save time. Yeah. If we use the surface to know methods, then we could directly using the uh, large selection to select these points or these lines, but there's not prefer for the shell to solid interaction because shell has 5 degree of freedom. It also have the rotational degree of freedom. If you're using the node to surface tie method, then actually you only tie the displacement instead of the well without the rotation. In order to apply the rotation coupling between the plate and the solid, we have to use this method. Yeah, but you could using yeah we will use surface to surface. Then this one is done. Then we need to build another one. Bottom also tie surface. Let's call it bobbed face. Also face. Then let's hide this face sheet again. Then we need to select that again. Okay. Select a bottom core one by one. Okay. If you select too fast, then this might happen, which means you select multiple other objects. Then you can always deselect it. It's not a big issue. Okay, after this 5 minutes of selection, we finished this surface to surface contact. And then now we also want a interaction with a surface to surface contact. Uh, to avoid this interaction, we use this surface to surface contact. No, self contact. Do we have general contact? Oh, we don't have general contact in standard. General standard. Okay, we'll build a contact with nothing in there. We want to have a self contact standard. Select all the surface here. Core surface. Surface to surface. Okay, great. Then in the loading condition. So first we want to calculate a bending. Yeah, bending is the most difficult one because it's difficult to apply a displacement control bending. There is also a tutorial to show you guys how to adding a uh, displacement control bending. So now, at first, because it's a symmetry one, we want to constrain its symmetric property. We want this to also get back. Great. So now we want a symmetric one. This one is X symmetric. And now we select this surface. Mm, okay, this surface, and also these boundary lines. They are under X symmetrics. Great. And then also Y symmetric. Y symmetric. Great. Let me double check. Oh, we forgot to call this X symmetrics. The name or read name. X symmetric. In order to apply let's say we're adding a bending in the uh, XOZ, YOZ plane. So we're bending along the Y direction. Then we need a coupling or yeah, coupling feature to couple this together. So first, let's build a uh, reference point. Let's select symmetry plane, that is 305. Y is 0, Z is 5 plus 25.5 because it's a half of 51, then it's 30.5. You can see the reference point here. And then we want to add the interaction. And to apply the loading, this one, coupling. This is X coupling, wall bending. The control point will be this one. X control. And the surface region will be this. Great. It will be X load. Right. We want to assign order degree. Yeah, because for solid we only have U1 to U3, but for plate we have all this rotation. Great. Okay. Contain both 3D shell and 3D shell edge is not yet supported. Then we just want these two coupling. We just want the top and bottom. This is the control point, this one, X control. Select it. Oh, I already used it. Then let me do that. Tool set. Manager. Choose control. Doesn't allow me to do that. Okay, then we just delete it and then create a set called X control again. This one, surface, X low, this one, and this one. Yeah, then now it allow us to do that. And we can only confine the U1, U2 to U3. I think it's acceptable because we can only add constraint on the surface plate. We don't directly add a loading on the core, so it's acceptable. Yeah, then we align all this displacement to the reference point here. Then we could load our reference point with rotation. Then we will say displacement. No, let's call it expanding. Displacement, rotation. Yes, exactly. Let's directly select this one. And then rotation along two direction. Then let's do it as one. For other constraints to get rid of rigid body motion, we already have XY symmetry. So the only thing we need to refine is the Y displacement. So we give a 0 Y displacement here, then all of the displacement it's well confined. Right? So you can see that it's a rotation along the y direction. Great. Then we do mesh arc. Let's change the element type here to be shell element. Yeah, good enough. S4R is good enough, shell element. Then we just mesh it. I think automatically it will have already good enough dense mesh for us. Yeah, then we just keep it like this. For the part, then because the face sheet is under banding, which is uh, tension and compression, right? So for banding, if we want to use linear elements, then we need to avoid shear locking. So therefore, we need to assign a thickness as more elements. We will use number 5 elements. Then we can mesh it. Wow, it's pretty coarse. Then the global size will be, let's say, 1. How about that? 1 is still very large. 10. How about 5? Yeah, then it's good enough. And this is our face sheet. Assembly look like this. Pretty good, no? Okay, great. And next we can build our model like this. Then we can calculate the whole process. And because of this calculation actually takes times, it has a plasticity. So previously I already finished one, so we can look at my previous results. Let's save this one as uh should be a sandwich. Yeah, I already built one. Let me open that one. And set our directory to one layer earlier. So here's the one that I already have the calculation complete. It's the same setup. Yeah, let's look at the results. You can see the bending in the uh, along the y direction. Let's draw some figures here. For example, stress. Yeah, the deformation looks weird is because actually we fixed the location somewhere here. Yeah, somewhere here. So it will when it bends, this one will go upwards, but this one will fix it the uh, original location. Yeah, you can see the effect how it bends. Let's go to the final step. Yeah, you can see there's a crash on the skin layer. Yeah, there are multiple things we could implement here. So first is adding the symmetry plane back to it. So we could add XD and YG symmetry. Then you can see the whole structure is modeled like this. Yeah, it's bending starting from here. So it's kind of like forming a uh, saddle shape. Yeah, because it's uh composite, so it could easily form a uh saddle saddle shape. let's look at some interesting information. For example, the plasticity. So here's the yielding point. Let's see when it start to yield. Okay, so in the PowerPoint slide, we said that the yielding will happen at the phase sheet, right? Let's see how it works. Then just in one step, the whole phase sheet is it's in yielding, but the core is still not in yielding. This is why showing that the phase sheet actually carrying the load. Now, with the whole process, you can see that actually evolving. Yeah, the yielding evolving from the core, from the center point to the outer region. Yes. If you look at the stress or plastic deformation, yeah, you can see the stress, S11 stress for the plate. That is, at first it's mainly on the surface, plate surface. Under one side is tension, the other side is compression, right? S11 should be in the uh, X direction. And 22 is almost zero for the plate. 33, it's only applicable on the, yeah. And if we let's select the instance, keep that. Yeah, but this is the base sheet only. We can look at the S11. One is tension, one is compression. S22, almost zero. It will have some boundary effects there. S33, yeah, have some boundary effects there, almost zero. S12 has some boundary effect there, almost zero. 13, yeah, but it's larger because it do undergo a little bit shears there. And 23 should be almost zero. Yeah, some shear loading is carried by the phase shift, but not so much. Yeah, if you look at the plastic deformation, it would say it's the loading point that has the largest plastic deformation. Right. Then the interesting part is if we go to the core. The core for S11, as we remember, that is for uh, in plane. So in the sandwich structures in plane direction. So there will be tension at top, compression at the bottom, similar as a beam structure. But there will be some periodic feature along the connection point. Then the stress is smaller. Yeah, in between the two connection, then the stress is higher, which is showing that actually forming a zigzag shape, a wavy pattern. Yeah. In order to show you the wavy pattern, you can see that here it actually crushed a lot, forming such a wavy pattern. In the early stage, it will forming a wavy pattern like this one, kind of like an Euler buckling effect, with the wavelength to be 1. If we want to see whether it's rotation or not, let's go to the deformation, rotation, or no, UR3. Yeah, UR3 should be the rotation along the z-axis. So you can see yeah, the back and forth wavy pattern of the core shell. Actually, it's undergo some compression causing like this. So it only forms in the compression region. The tension region wouldn't have that kind of uh, wavy pattern. In the compression, they will have Euler buckling, and also they will have a large amount of stress, a shear. The shear we will look at the 1-2 direction. Yeah. The shear is way larger than the value of the plate. So let's go to the last step. The shear here is the 800 ish. If we go to the plate, then we need to go to 1-3. It's still 800 something. It's comparable because it's the same materials. Yeah, just keep in mind that the S something something is different for plate and solid element. Okay, that's the one for the compression, and we do see that it has a very interesting failure mode. We can also see some shear band there. If we click on this, it will be even more interesting. Yeah, yeah, it will bulge out. Yeah. Okay, so later let's see whether we could formulate it. This one, explosion. Then we need to get back to here, get back to the model itself. So for that kind of loading, actually we need a different steps. We need a dynamic explicit steps. Large deformation, yes, yes. And this one wouldn't change that. And go to the interaction. Now I will need to build another reference point at 0, 0. Let's say 150. So there will be a reference point 3 here. Oh, shoot. Let's generate way too much reference point. Maybe using the features. I should have a reference point uh, control assembly features. Yes, I have multiple reference point. Let me delete this too and change this one to the name TNT. I will use TNT to blast the plate. Here we need to build an interaction. Here we use incident wave. Definition will be air blast. This is the ConWeb charge. It's kind of like a U.S. military data set that tells us that what kind of TNT that related to the apply loading. So here, because we are using millimeter, so we need to use millimeter set. So we just want to use 3 kilogram of TNT. That would be, and conversion mass to kilogram, that would be 1,000 because it's in ton. Conversion for length to meters, then is also 1,000. Conversion time to second is 1. Yeah, unity. Conversion pressure to Pascal, then would be 6 times 6 power to 6. Okay, great. Then we need to build a interaction instant wave. Step 2. Here, we select the reference point here. TNT. Then we need to select a surface for the region. Then we use the last surface. Then we select this surface. Great. You will see a box like this. 0 here. Magnitude 1. Yeah, convex. Oh, then we need to change the steps because the blast happening pretty fast. Then we want to change the time to be 1.5 e minus 3. Yeah, 1.5 milliseconds. Okay, then we had to modify the loading condition. For this one, this two, we just need to let's click on the steps. Load. Let's move this two to the initial steps. Yes, let's move left. And also this one, move left. Then it should be fine. This one, the X symmetry and Y symmetry. And this one, turn it off. And we go back to the steps. Then we also want to fix this two region. We use displacement and antisymmetrics. Blast. Fix. Choose. No, we just need to choose these two because we can only confine the play instead of control the play instead of controlling the core. Then we want to encapsulate. Then we should able to calculate this one. We don't need to change the mesh. Yeah, it should be fine. We'll create a job 2. Let's use parallelization. At least 2. We need to generate a field output. Okay. Do we have anything by default? We have the default option. No. And I need to turn on the step 1 to see. Not in sequence. Okay. Let me copy this. Also for history output, we create one. Pre-select default. Okay, great. Oh, how many time step it requires? Interval 200. Now every time step. Okay, great. Now let's do the calculation. I haven't tried this before, so let's see whether it can run. Okay, it can run. It just has some warnings. Let's see how long it takes to calculate the first step. Oh, in 1 second it calculated. That's it works. For this tool, we don't need it anymore. Just turn it off. We have our steps, time of detonation. Let's see the warning sign. Warning message. It's not working. Okay. Since the calculation took so long, I finished the calculation and put the result here. So, with the TNT air blast, the sandwich structure will behave like this. Yeah, the form like this. And if you remove the face sheet, you can see the core actually crushing like this. Great. But this is explicit dynamics. It's less trustworthy, but it's under a high string array domain, so it's almost the only way that we could calculate this problem. Yeah.